To proceed from where we had left in our previous lesson, we want to go to something else, and what we want to discuss today is relative atomic mass and isotopes. So we want to majorly engage in looking at relative atomic mass and isotopes. And I'll begin my discussion by first trying to unravel the meaning of isotopes, so that from there we can be able to proceed to defining the relative atomic mass. So what are isotopes in a chemical language? Isotopes will always be able to get referred to as atoms of the same element, which have the same atomic number, preferably number of protons, but different mass numbers. Look at that definition. So isotopes are atoms of the same element which have the same atomic number, which is the same as number of protons, but different mass numbers due to the difference in the number of neutrons. Due to the difference in the number of neutrons. So as long as they are atoms, fine, and these atoms are of the same element. So different atoms, which can either be 2, 3, or 4, 5, but those atoms are of the same element. Because I told you an atom must be found inside an element. So I can have this example. I may have this, look at that, as my element, and I'll have these atoms here. So look at this example. This is an element, the whole of it, but inside this element we have atoms. So these are atoms of the same element. So two atoms of the same element. So the element is one, but the atoms are two. So they are atoms of the same element. So when someone talks about isotopes, the person is referring to atoms which are of the same element, and those atoms of the same element have the same atomic number or have the same number of protons, right? So these two atoms of this element have the same atomic number or have the same number of protons. But when you look at their mass numbers, they are different. So the difference occurs in the mass numbers. But the atomic number or number of protons is the same. So atoms, which can either be 2 or 3, you can even be having 4 or 5. As long as they are atoms of the same element, and those atoms have the same number of protons or have the same atomic number, but the mass numbers are different, they qualify to be called isotopes. Wow, so the difference in the mass numbers will occur when there is a difference in the number of neutrons. Yeah, so atoms of the same element having the same atomic number or number of protons, but having different mass numbers. Why are the mass numbers different? Because of the difference in the number of neutrons. So same atomic number, different mass numbers. Why? Difference in the number of neutrons. So that is all about isotopes. I can give examples. For example, I can have an element like carbon. Carbon is isotopic. That is to mean it actually ends up having several isotopes. Very good. So I can put here 12 and I put here 6. I put here 14, I put here 6. What did I tell you in my previous discussion? I said the number written as a superscript, this one here, is always the mass number. But the number written as a subscript or the number written at the bottom here will always serve as the atomic number or the number of protons. So what did we say? We said mass number is equals to protons plus neutrons. Okay, what is our mass number here? In this case, the one actually written as the superscript, it is actually 12. Number of protons, the number at the bottom here is referred to as atomic number or number of protons. I can be able to put here 6. Then I say plus. So I'll obviously know that 12 is equivalent to 6 plus 6. So number of neutrons is 6. Let's come to this other example here. Mass number is equals to protons plus neutrons. Mass number 14. So is equals to protons P. The 6 at the bottom here. This 6 here. So you'll write here 6 plus neutrons. Obviously 14 is equals to 6 plus 8. So let's give this definition. These are called isotopes. Why are they isotopes? They are atoms but of the same element. Which element is this? Carbon, because of the C and the C. So two atoms or atoms of the same element called carbon having the same atomic number. Look at that. The same atomic number or the same number of protons, but different mass numbers. Different mass numbers. Look at that. So the atomic number is the same, which is 66, or the number of protons. But the mass numbers are different. The mass number is 12, and the mass number here is 14. So same atomic number, but different mass numbers. Different mass numbers. Why are the mass numbers different? Because the number of neutrons are different. Look at that. So atoms of the same element, same atomic number or same number of protons, but different mass numbers. Why? Because of the difference in the number of neutrons. Correct. So let's go to something else, and this is what we refer to as relative atomic mass. We preferably refer to it as RAM. RAM. So RAM has actually been able to get used in determining the mass of an atom of an element. And it is called relative atomic mass. Relative atomic mass. That is to tell you that you want to get the atomic mass, or you want to get the mass of an atom, but relative to. That means you cannot just estimate the mass of an atom. You must get the mass of that atom by comparing that atom to another reference atom. Of course, I can decide to say, I can put here hydrogen, for example. Then I put here sodium. And if I want to get the mass of an atom of sodium, or the atomic mass of sodium, I should compare the atomic mass of sodium to another reference element, like hydrogen. So relative. Of course, a relative is a person whom you are actually related to. So you can only be able to get the mass of an atom of a particular element relative to another atom of another element. So you can get the atomic mass of this sodium, or the mass of an atom of sodium, relative to the mass of an atom of hydrogen. So relative atomic mass. And of course, you can be able to actually do that in a very easy way. So when scientists were trying to get the masses of atoms of elements in chemistry, they actually decided to pick hydrogen as the reference element. That is to tell you that they could get the mass of any element, let me even say X, relative to another element like hydrogen. So they could always get the mass of an atom of a particular element, be it sodium, magnesium, aluminium, calcium, but now relative to a particular element, which could actually serve as the reference point. And the element they first used was hydrogen. Now, why was hydrogen used as the reference element? Because it was the lightest atom in the periodic table, with one atomic mass unit. So they might ask you, why do you think getting the atomic mass of a particular element could always be able to rely on hydrogen, because you know hydrogen is the lightest atom in the periodic table. So if hydrogen becomes the lightest atom in the periodic table, they can get the mass of another element with reference to that hydrogen, which is actually serving as the lightest. So it was the lightest atom in the periodic table. That's why it got used as the reference atom in determining the atomic masses of other elements. And let me give you an example. Assuming I actually want to get the atomic mass of a particular element, we could use an instrument called mass spectrometer. So mass spectrometer was used as an instrument of determining the atomic mass of elements. A mass spectrometer was an instrument that got discovered by scientists, and it got used in determining the atomic masses of elements, or atomic masses of atoms of elements. So if this one becomes my mass spectrometer, and I put here hydrogen, one atom of hydrogen, then I put here one atom of sodium. Preferably, I know I'm going to put here 23 hydrogens, because I've told you, hey, hydrogen has one atomic mass unit, so its mass is 1. But you know very well sodium weighs 23 grams. So to actually balance this, in as far as this mass spectrometer is concerned, I'm going to put here 23 hydrogens so that they can actually be able to balance one sodium. 23 hydrogen atoms balancing one sodium atom. So if you put here 23 of them and it balances, that tells you the mass of sodium is 23. So this is how a mass spectrometer works. They could pick an element or an atom of an element like sodium, they put at one point, then they could actually pick hydrogen, the lightest one, with one atomic mass unit. They put it on this other side. Of course, they will not balance if it's 1. So they have actually to add hydrogen atoms until the sodium is balanced. So they could realize that at the end of the day, for example, in this case, 23 hydrogen atoms could balance one sodium atom. So they could easily be able to tell the mass of one sodium atom because of the balancing in terms of how many hydrogen atoms have been used. Now, because of that, they actually ended up defining RAM as, in terms of this, as the mass of one atom of an element relative to, okay, relative to one hydrogen atom. Very good. So they could tell the mass of one atom of an element. In this case, we have used sodium. We want to get the mass of one atom of an element, which is now sodium, relative to the hydrogen atom. Get the point? So you say relative to or compared to. You see, so the mass of one atom of an element, for example, sodium, compared to the mass of a single hydrogen atom. That gives you what you call RAM. Very good. So they actually left out hydrogen because of some complications like it existing as an isotope, because you have 3 isotopes of hydrogen. We have what you call deuterium, tritium, and of course you have what you call tritium. So the protium, the deuterium, and the tritium made it so difficult for scientists to really again rely on hydrogen as a reference atom in terms of determining the RAM of other elements. So a question can actually get framed in this manner. Why do you think scientists had to leave out hydrogen in as far as determining the RAM of other elements is concerned? What do you say? You say it's because it exists as isotopes. So it has several isotopes. It is actually isotopic in nature. It has protium, tritium, and deuterium. That makes it so difficult for us to actually get confused in terms of trying to see which one we rely on in getting the RAM of other elements. Now, they ended up now relying on oxygen. But again, oxygen brought problems because oxygen is also isotopic. Why? Because we have 16 oxygen and we also have 18 oxygen. Sorry, so 16 oxygen and we also have 18 oxygen. So it brought again problems. The mass number is different, but the atomic number is the same. So there are isotopes of oxygen. So because oxygen is isotopic, it could again not get relied on in determining the RAM of other elements. It could not get used as a reference element. So because of that, they ended up relying on carbon. They relied on carbon, and carbon was relied on as the reference element because of two very important reasons. One, carbon is very common. It's a very common element. If you look at the wood, it has carbon. Because plants manufacture food using carbon dioxide, so there must be carbon in the plant. Human beings have carbon because we feed on carbohydrates, proteins, fats. They contain carbon because they are manufactured in plants, which rely on carbon dioxide during photosynthesis. When you look at paper, which comes from trees, of course, it has to have carbon. Even some paints and inks are made using what you call carbon black. So at the end of the day, you realize that carbon is a very common element. It's a very common element. So common element, that is one. Two, it is very stable. It's very stable. So a very common element and very stable. That's why scientists rely on it to actually determine the RAM of other elements. So of course, at the end of the day, now you can be able to define RAM as, now if you are actually referring to carbon, the average mass of one atom of an element, average mass of one atom of an element compared to 1/12 mass of an atom of carbon 12. Because carbon is also isotopic, by the way. We have carbon 12 and carbon 14. That is actually using what you call radioactive dating. So RAM is the average mass of an atom of an element under consideration. So there must be an atom of an element that you really want to determine its mass. So you are actually getting the, what is RAM for information? Average mass of an atom. So look at this, average mass of an atom of an element. But now you're comparing that to, or you're getting that average mass of that atom of that element to 1/12 mass of an atom of carbon 12. A good example. We have carbon, we have magnesium, right? We've said average mass of an atom of an element. So let's say carbon is 12. Okay, magnesium is actually, let's see, 24. Correct. So we'll come here and say average mass of an atom of an element, you see, compared to, look at that, 1/12 mass of an atom of carbon 12. So you'll say 1/12, you see, 1/12 mass of carbon 12. So times that mass, 24. What are you going to get? You should actually get the RAM of this atom of magnesium. So you can say average mass of an atom of an element, look at that, relative to 1/12 mass of carbon 12. So because this and this will disappear, the resultant mass just ends up becoming 24. So average mass of an atom of an element relative to 1/12 mass of carbon 12. So of course that's times that mass. Look at that. Average mass of an atom of an element relative to 1/12 mass of carbon 12. 1/12 mass of carbon 12. Correct. If that becomes the case, then you can be able to actually end up saying that now RAM is average mass of an atom of an element, for example magnesium with a RAM of 24, relative to 1/12 mass of carbon 12, relative to 1/12 mass of carbon 12, relative to 1/12 mass of carbon 12. That gives you what you call RAM. That gives you what you call RAM. Now, okay, let's proceed forward, and we'll need to actually do some calculation in terms of getting the RAM of an element. And you can get a question telling you that you have an element X, but this element X has 3 isotopes. The first isotope is X22, the second one is X24, and the third one is X25. The first one The percentage abundance is 89.6, the second is 6.4, and the third is 4.0. So I want to get RAM. What do you say? What do you say? You'd say mass of isotope times percentage abundance plus mass of isotope times percentage abundance divided by 100. You can be mass of isotope times percentage abundance plus mass of isotopes times percentage abundance plus mass of isotopes times percentage abundance, depending on how many isotopes are here. For example, here we have three. We have three isotopes. So we are supposed to say mass of isotopes times percentage abundance plus mass of isotope times percentage abundance plus mass of isotope plus this then times percentage abundance divided by 100. So let's begin our business. Mass of isotope for the first case, 22 times percentage abundance, 89.6 plus mass of isotope, 24, percentage abundance, 6.4 plus mass of isotope, 25 times percentage abundance, 4.0. Then we say divide by 100 because the total percentages must add up to 100. So if you say 89.6% plus 6.4% plus 4.0%, it must be 100%. Must be 100%. So we shall pick our calculator and plug these values into this calculator for us to get the answer. I don't know if it's actually able to get seen. Let me try and see. Okay, that's well and good. So we shall begin 22.0 times 89.6 plus 24 times 6.4 plus 25 times 4, and say divide by 100. You get 22.248. So our RAM becomes, so it must be an average value actually, is equals to 22.248. It does not have units because it is actually a ratio. You are getting the mass of an atom of an element relative to another reference what? Atom of an element. So you cannot actually put here units. It's actually a ratio. So it's actually 22.248. And you always say that the RAM of an element must be as close as to the one that's most abundant. It is 22. Look at that. So we have three isotopes. We have this isotope, this and this. But which one is the most abundant? The X22 is the most abundant. Why? Because it has the highest percentage abundance of 89.6. So the RAM of this element must be close to the most abundant. So the most abundant is 22. So that's why our answer is 22.248. The answer 22, okay, 0.248 is closer to the most abundant. Look at that. That's the highest percentage. So the answer must be 22 point something because of the highest percentage that this isotope has. That can tell you whether you've gotten the answer or not. Yeah, literally, and that's what you're supposed to do, and that gives you the answer. Okay, I guess you can actually be able to get a different concept, and this can demand that you're going to use what you call ratios. For example, someone can tell you that you have chlorine 35 and chlorine 37, and the ratio of these two isotopes of this element called chlorine is 4:1. Someone asks you to get the RAM. What do? You'll say mass of isotope times ratio. You don't say percentage abundance, of course, plus mass of isotope times ratio. Then you divide by total ratio. Then you can be able to get the answer. Let's begin our work. Mass of isotope 35. The ratio, it is 4, plus mass of isotope 37. The ratio 1. You divide by total ratio. You say 4 plus 1. That gives you 5. So let's see what is the answer in this case. So I have 35 times 4, okay, plus 37 times 1, that is right. Yeah, and I say divide by 5. What do I get? 35.4. 35.4 is my answer. So I have 35.4. So look at that. So this RAM 35.4 is closer to the most abundant because isotope 35 has the highest abundance with a ratio of 4, but isotope 37 has the lowest abundance with a ratio of 1. So 35.4 becomes our answer because it is closer to the most abundant, which is 35, that has a ratio of 4 as the highest ratio, because the other ratio is 1. So that tells you more about you knowing whether you've gotten the right answer or not. I guess you've had a chance of understanding how you really maneuver around to actually get the RAM of an element if you have different isotopes that have to get tabulated for you to get the RAM of that element. There's something called an ion, and for this case, an ion, for your information, is just a charged particle of an atom after an element has lost or gained an electron or electrons. Now let me begin from here. When someone says an ion, I-O-N, not I-R-O-N, that's where people actually end up getting confused. An ion, I-O-N, is a charged particle. Okay? And it must be a charged particle of an atom. So an atom which is charged. So it must either be positive or negative for your information. So it is a charged particle of an atom, or an atom which is positively charged or negatively charged after an element. Of course, an atom is found inside an element, so that actually makes sense. After an element has lost or gained. So you either lose or gain for you to become positively charged or negatively charged if you're an atom. After an element has lost or gained an electron or electrons. So a particle which is charged after an atom has lost or gained either an electron or electron. So it can either lose or gain an electron or electrons, which is more than one. So let's give an example of chlorine. Chlorine is number 17, and its electron configuration is 2 to 8 to 7. We said the first energy level must have 2. The second energy level must have 8. The third must have 8, but this one has 7. So it must actually end up gaining 1. You see, first 2, second 8, third 8, but it has 7. So it must gain 1. So it will end up having this as the resultant charge. Negative means negative means negative means negative means gaining. Negative means gaining. So you'll either find this 1, 2, 3, 4, 5, 6, 7. So from this end, the whole of this, if you find an element to the outermost has 2, 3, or 1 electrons, it must lose. If you find an element has 5, 6, or 7, it must end up gaining. So here, lose, here, gain. Look at this, 7, gain. And once it gains, it becomes negatively charged. Once it loses, it becomes positively charged. So let me use this example. Here, we have 7 in the outermost. This 7 can be seen here. So this should be your scale. Look at the outermost. What is it having? 7. Come to your scale. Where is 7 found? At the bottom. So is it going to lose or gain? It must actually end up gaining. And after gaining, it must develop a negative charge. So you have to ask yourself, how many is it going to gain? It must have 8, but it has 7. Why? It is not stable. So what does it do? It ends up gaining 1 for it to have 8. So it ends up having a single negative charge. Okay, I may have an element like aluminium, which is number 13. The electron arrangement is 2 to 8 to 3. So let's look at the outermost, 3. So if there's 3 here, let's go to the scale. Where is 3 existing? 3 is here. So 2 to 8 to 3. So it has 3 to the outermost. So it must lose. because 3 is here, so it must lose. So it must develop a positive charge. So I can come and say now aluminium, then I write my 3, then I write my positive charge. That tells you it has lost 3 for it to be stable. So you have to ask yourself, the first has to have 2, the second has to have 8, the third has to have 8. But now it has 3. So it is either going to gain 5 or lose 3. So you preferably pick the smaller one. Why? Because it is actually very hectic and it requires more energy for this atom to gain 5 than to lose 3. So it's easier for it to lose 3 than gain 5 because of the difference in the amount of energy required in each case. So that tells you that now it is easier for it to lose 3. So it preferably ends up losing. That's what the scale tells us as far as this part is concerned. So it loses 3. So on losing 3, it develops a positive charge. So it ends up having Al3 positive to mean it has lost 3 electrons. Cl negative, it has lost 1 electron. No, it has gained 1 electron. And here, it has lost 3 electrons. Negative is losing. No, negative is gaining. And positive is losing. Okay, so that is actually what you're supposed to know as far as this part is concerned in terms of the ions. You want to know whether an element is going to be an ion with a positive or a negative charge, please know its atomic number or number of protons, write its electron configuration, look at the outermost number of electrons, ask yourself in as far as this scale is concerned, is it going to lose or gain? Once you know it's actually going to lose, for example, you must indicate a positive sign with the number of electrons lost, if they are 3, 2, or even 1. If it is going to gain, ask yourself, how many is it going to gain? Is it going to gain 1? Is it going to gain 2? Is it going to gain 3? You have to indicate that number with the charge, which is negative because of the gain. Yeah, that is it. And maybe lastly, before you can be able to conclude on this, you might be told maybe to come up with different compounds in chemistry. I'll just use 2 examples to explain how you can be able to form compounds in chemistry. And the first example can be this. Someone has told you to write down the formula of aluminium sulfate. I don't want to talk much about radicals because you must have had a chance of discussing this somewhere. And of course, a radical is a group of atoms with a charge or with a net charge, and exist and react as a unit. Hey, a good example can be this. Sulfate. SO4 2 negative. Look at this. This is a radical. It is a group of atoms. How many atoms are here? 2. Sulfur and oxygen. Sulfur atom, oxygen atom. So a group of atoms which are existing and reacting as a unit, but they have a net charge of 2 negative. A group of atoms that exist and react as a unit with a net charge. Correct. Exist and react as a unit with a net charge. So a group of atoms that are existing and reacting as a unit with a net charge. They have a net charge of 2 negative, but the atoms are existing and react as a unit. So we want to come up with aluminium sulfate. I'll first come here and write Al. I'll write SO4 2 negative. We need to know the charge of aluminium. So we shall say number 13. So that will be 2 to 8 to 3. I told you with 3, it actually end up losing. So it will actually develop a positive charge. So literally, you can now come here and say aluminium 3 positive and sulfate 2 negative. We shall interchange these oxidation numbers or states. Okay, we shall come here and say now this and this will this and this. Okay, so we shall have aluminium. Look at that. This 2 drops here. There's 2 negative here. So there's what we call the interchanging of oxidation states or numbers. So the 2 drops here. So aluminium will have 2. And then we shall write SO4. And there's 3 that drops here on SO4. So the SO4 must be put in brackets and you put 3 outside. This becomes aluminium 3 sulfate. Aluminium 3 sulfate. So you can say aluminium 3 sulfate or aluminium sulfate. there's that aspect of determining the radical and know its oxidation state. You should also know that other element, know its outermost number of electrons, determine its oxidation number, and be able to interchange those oxidation numbers, then come up with the formula of that compound. That's aluminium sulfate. Aluminium sulfate. Aluminium sulfate. So unless you have a question, that's the much you can discuss for today, and have a blessed day.